Welcome back. In the previous lecture, we took first steps into the state space of qubit pairs. In this lecture, we continue to explore the 2-qubit state space. So this hit bra for the singlet state is a particularly neat statistical operator for the 2-qubit system. And it clearly does not separate easily in something that only belongs to the first qubit, only belongs to the second qubit. But we could, of course, begin with something like this. We could begin with a row 1 for the first qubit, which is of the form 1 plus S1 dot sigma. And now I will notice that this is sigma 1. And for the second qubit, we have half of 1 plus S2. Dot sigma, and now this is the sigma for the second qubit. And if I just multiply this together, the row 1 and row 2, the kind of structure I get is a quarter, and then we have 1 plus S1 dot sigma 1 plus S2 dot sigma 2, just by multiplying these pieces. And there's one more term, which is sigma 1 dot S1 and then S2 dot sigma 2. So it's a term that only involves sigma 1, it's a term that only involves sigma 2, and it involves a term that has the sigma 1 and the sigma 2, and in between something that has the structure of a dyadic. So it's a dyadic is like a double vector. So it's a vector on the left that you can dot into sigma 1, but it's also a vector on the right that you can dot into sigma 2. Now imagine that you have this kind of row 1 and row 2 product with one choice for S1 and S2 and then the product like here. Then you have a second one and you take a convex sum. And the convex sum will have one such term and one such term. But here you will have a dyadic that is made up of such an S1, S2 dyadic product and a different S1, S2 dyadic product with a different weight. And so you will get something more complicated. In fact, in the singlet cat bra, we also have such a structure with a dyadic, namely sigma 1 dotted into the unit dyadic dotted into sigma 2. Now the unit dyadic is of course exactly what you think it is. You dot the unit dyadic into a vector on the right, it reproduces that vector. You dot it into a vector on the left, it reproduces that vector. So it just does what a unit operation is expected to do. In this particular structure, we just have a product of something goes by row 1 and row 2. So this is what we call a product state. And we can now think of making up a general 2-qubit row by a weighted sum, weights WK, and then a product of the row 1, row 2 kind, but of the kth product. So S1, S2, S1, S2, well, there's one for k equals 1, there's another one for k equals 2, there's a third one for k equals 3. And these are just positive weights of unit sum. So this is a convex sum of 2-qubit product states. Now, this particular state that we have here for the singlet is not of this kind. 2-qubit state that is such a convex combination of product states is what we call separable. The states which cannot be written like this, the states which are not separable, are called entangled. So here's the statement that I want to make. If the 2-qubit statistical operator, row 2-qubit, is the convex sum of product states, if it is of this particular form, then the state is called separable. Otherwise, it is entangled. So you can think of the separable states as being made up of products, and in each product the two qubits have individual properties, and we just mix them up in some mixture and get a general separable state. But we can kind of decompose it into pieces where each piece is of a product form. So in each piece the qubits have individual properties. However, if you have an entangled state, then this is not possible. And you cannot assign individual properties to one qubit or the other. The qubit pair as a whole has certain properties, like in this singlet state, but in the singlet state, the individual qubits do not have well-defined properties. So if we have a product state, we have this Bloch vector for the first particle, the Bloch vector for the second qubit. We have this dyadic structure that involves the sigma operators of both qubits. If we have the singlet ket bra, we don't have these terms, but we have a particular sigma 1 dot sigma 2 that involves the unit dyadic. So what's the general structure of a two-qubit state? Well, what can we have? Okay, so we need the unit operator, because that gives trace to the statistical operator, which has to have unit trace. So all the other pieces will be traceless. And then there will be a term of this kind, sigma 1, and a term of this kind, sigma 2, and there will be a dyadic term, C1, and then the cross term C and sigma 2. And how do I know that this is all we can have? Well, we know that because we know that all functions of a sigma operator are a linear function of the sigma operator. So now we have two sigma vector operators. So we need something that is at most linear in each of the sigma vector operators. So we can either have terms that do not involve the sigma vector operator at all, like this one, or here not involve the sigma 2 operator, not involve the sigma 1 operator, or involves the sigma operators once. And so this involves the sigma 1 operator once, this involves the sigma 1 operator once, this involves the sigma 2 operator once, and this involves the sigma 2 operator once. But there's no room for more complicated terms where you have two factors of sigma 1 or two factors of sigma 2. So this is the general structure. And so this is a 3 vector, and this is also a 3 vector, and this is a 3 by 3 dyadic. So in total we have 3 plus 3 plus 9, which is 15 parameters in total. So the two qubit states are substantially more complicated than the single qubit states, where we only have 3 parameters for the S vector. Here we have two S vectors, 3 parameters each, and we have this cross dyadic which has 3 times 3 parameters. So in total we have 15. So the S1 and the S2 vectors, the two Bloch vectors in the general two qubit states, are obtained by calculating the expected value of the sigma 1 vector operator and the sigma 2 vector operator, which means we multiply with the statistical operator, we take the trace. So this gives us the expected value of the sigma 1 vector operator and the corresponding value for the sigma 2 vector operator. And for the cross dyadic that appears here, well, we have the dyadic product of the sigma 1 vector operator and the sigma 2 vector operator and the expected value of this product. So this is sort of familiar. Here we will get a 3 component vector, which are the expected values of the x operator for the first qubit, of the y operator for the first qubit, and finally the expected value for the z operator for the first qubit. And likewise for the sigma 2 expectation values. I'm not going to write this down. So here we have a dyadic product, and in the dyadic product it's always most natural to think of the first vector as a column and the second vector as a row. So you get a column times row product, and that will be a matrix. And so what we have here is a 3 by 3 matrix where we have x1, y1, z1 for the column, and then for the row we have x2 and y2 and z2. So these are the entries in the first column, where we have the column for sigma 1 and the first entry of the row for sigma 2, which is the x2. And then the next column has x1, y2, y1, y2, and finally z1, y2. And for the last column, we have x1, z2, we have y1, z2, and we have z1, z2. So as you can see, the sigma 1 is a column x1, y1, z1, x1, y1, z1, x1, y1, z1, and the sigma 2 is written as a row, x2, y2, z2, x2, y2, z2, x2, y2, z2. And so this then is a 3 by 3 matrix, that is the matrix representation of this dyadic, such that this column represents this vector, this matrix represents this dyadic, and there is also a vector for the sigma 2. And again, we can count parameters. This is 3 parameters. This is another 3 parameters. And this matrix has 9 parameters, 9 expectation values. Together is the 15 parameters that we counted earlier. In summary, there are separable and entangled 2-qubit states that reside in the 15-dimensional state space. In the next lecture, we apply this machinery to the Bell scenario and observe again that there are quantum correlations that do not obey Bell's inequality.